inductive step. Inductive step. Here we show that the conditional statement Pk implies Pk plus 1 is true for all positive integer k. Okay. Now you can see mathematical induction consists of two steps. One is basic step, another is inductive step. Here, to prove a general statement Pn is true, to prove that a statement Pn is true for every value of n, the induction method has two steps. In the basic step, we simply verify that P1 is true or not. Means first the proof is initiated or not. After that, in the inductive step, we assume for Pk and shows that Pk implies Pk plus 1 is true. Okay. Then, in terms of mathematical induction, we can say the statement is true for all the value of n. Now, looking into this, we can solve one example. Using induction so that 1 plus 2 plus 3 plus up to n equal to n into n plus 1 divided by 2. Now, for proving simply we want to show that this is true for any value of n. So, for that one, using mathematical induction, our first work is to define the prepositional function. Prepositional function, which one? Look here, we simply define the prepositional function Pn. Pn as 1 plus 2 plus 3 plus up to n equal to n into n plus 1 by 2. Now, to prove Pn is true for all the values of n, we will go with two steps. Which two steps? The basic step and inductive step. Now, our first step is basic step. Here, we simply verify that P1 is true or not. So here, we verify that P1 is true. That is, now you can see that Pn equal to this much. So what about P1? P1 statement will be 1 equal to 1 into 1 plus 1 divided by 2. Now, from this you can say that as we can see that 1 into 1 plus 1 divided by 2, that is equal to 2 divided by 2 equal to 1. So, P1 is true, is verified. Thus, the basic step complete. Right? That means in the basic step, what do we do? We simply verify that the statement Pn is true for n equal to 1 or not. That's simply as verification we can see. Now, in our next step, for the inductive step, we will go with inductive step. Our next step, second step is inductive step. Here, In the inductive step, what we need to do? We assume for Pk and so for Pk plus 1. That means to complete the inductive step, we need to prove that Pk implies Pk plus 1 is true. Now we need to prove this. Now for that one, what we take? We assume first. We assume that Pk is true. Now after assumption, what can you say? As Pk is true, that is 1 plus 2 plus 3 plus up to k equal to k into k plus 1 divided 2 is true. This is our assumption. Now we need to show for Pk plus 1. Now you can see that now 1 plus 2 plus 3 up to k plus 1. This can be written as 1 plus 2 plus 3 up to k and plus k plus 1. Now as we are saying that 1 plus 2 plus 3 up to k equal to this much is true. So in this place we can write for k into k plus 1 divided by 2 and this k plus 1 is as such. Now from here little bit simplification, you can take k plus 1 outside common. So we have k divided by 2 plus 1, or this gives k plus 1 into k plus 2 divided by 2. Now you can see that, now we can see that what p k plus 1 is true. How we can say that Pk plus 1 is true? Look here. What you can say Pk plus 1 statement? Pk plus 1 statement is nothing but 1 plus 2 plus up to k plus 1. That will give n into n plus 1, that is k plus 1 into k plus 2 divided by 2. This is the Pk plus 1 statement. Now you can see that 1 plus 2 plus 3 to k plus 1 is getting it this much. Hence, we can see that Pk plus 1 is true. Now as the last, what can you say? Now as Pk is true, we have taken and get that Pk plus 1 is true. So by direct proof our Pk implies Pk plus 1 is true, and hence the inductive step complete. Okay, since our both basic step inductive step complete, so now what you can say, as both the basic step and inductive step has completed, so by method of induction we can say that